Thank you everyone for joining us. I have the great pleasure to introduce Katie Steckles, who is a mathematician based in Manchester, who gives talks and workshops and writes about mathematics. She has finished her PhD in 2011 and since has talked about maths at universities, schools, events, festivals, on the BBC radio and TV, in books and on the internet. But if that has already caught your attention, you might know her because she's one of the brains behind the Math Jam, which happens worldwide, which also happens today. And I think with further ado, I will just pass over to Katie, who will present on puzzles with bridges.
Thank you very much. Yeah, so just to pick up on what Tiago was saying there, I am one of the organisers of Maths Jam. If this is not something you've heard of, this is an event which started in the UK several years ago, and the idea is that we get together and we do essentially this kind of thing. We share puzzles and we talk about maths and we have a bit of fun. And there is a website, if you're interested in Maths Jam, there's the website at mathsjam.com where you can find out more. If that is useful to you, then I've put those links into the chat. Anyway, hello everyone. My name is Katie and I am a mathematician and I talk about maths for a living. And I thought I would share something with you today that is, I guess, something that I thought was interesting. Essentially, I kind of wanted, like I was looking at various things on the internet. I saw this and I thought, actually, that's a really nice kind of example of a particular type of thing that happens quite often in maths. So it's sort of a puzzle, and it's really unfortunate because I know how important it is if you give people a puzzle not to spoil the puzzle for them. But unfortunately, I'm going to have to spoil the puzzle because I need to talk about it. But hopefully this will give you some thoughts about other things that you can think about as well. So I'm going to share some slides because I've got the puzzle on some slides here. Hopefully that is visible. The puzzle is essentially set up, it involves some bridges. There are, of course, more famous puzzles that involve bridges that you may be familiar with, but this is a slightly different puzzle. So instead of the 7 bridges of Königsberg, this is a puzzle with 5 bridges. Okay, so here is a highly technical diagram which I've drawn that shows a set of 5 bridges crossing a river, and there are islands in the middle of the river, and there is a person standing on one bank of the river. And the puzzle, I guess, that is involved in this situation goes as follows. An adventurer wants to cross the river. However, there has been a bad storm overnight and any or all of the bridges may have been washed away, each with a 50% chance. So for each bridge separately, there is a 50-50 chance that the bridge has been washed away by the storm. What is the probability that they can cross to the other side of the river? And, you know, it's a nice little question. You know, it involves potentially there's more than one route that they could take. So, you know, if the bridge immediately in front of them has been washed away, they might be able to walk along and cross this bridge instead and get across that way. Even if multiple bridges have been washed away, there might still potentially be a route there. And this is the kind of problem that, you know, you often see these kinds of puzzles, and I've given this puzzle to people at Maths Jam and at various other different occasions. And the thing about this, and I imagine some of you have probably already started doing this in your head, is that your instinct is to go, okay, how many different possible paths are there? And if certain bridges are washed away, how does that affect the probability? Like, which of the routes are affected by which bridges being washed away? And, you know, which of them are completely knocked out by one bridge and which ones require multiple bridges to be washed away in order for them to be impassable? And the number of different combinations and possibilities here suddenly seems quite big and quite complicated. And in fact, you can do it that way. You can sort of work out all of the different possible combinations. I think there are 32 different ways that the bridges could be washed out or not washed out, because each one of them is washed out or not. I guess it's 2 to the 5. And then you can look at, you know, which ones of those still allow you to cross the river, and you can work it out that way. But the thing about this problem is that there's slightly more to it than it seems, because doing that calculation is sort of, it's a slightly naive approach, because there are different combinations of bridges that could be washed away. So for example, if none of the bridges get washed away, there are multiple routes that you could still do. So you have to kind of try and not double count things, and it gets a bit messy and horrible. And if you do the calculation, it's possible to get the wrong answer that way. And I think you get something like 75% if you do it kind of piece by piece like that. But the thing you have to remember is that this is a problem being presented at a gathering of the gardener thing, right? So it's obviously there's something subtle going on here. There's something more interesting going on here. It's sometimes referred by people, proof by maths jam. Like, you're telling me about this, it must be more interesting than I think it is. So the thing about this puzzle is that it's actually one of two puzzles. And the second puzzle looks like this. So this is the same arrangement of bridges, but the question now is an adventurer wants to row down the river, but their boat can't get past the bridges. So there's some kind of low, I guess, bridges that don't open. There has been a storm overnight and the bridges may have been washed away, each with a 50% chance. What is the probability that they can succeed in rowing along the river and getting to the other end? And, you know, this is a different puzzle. I guess it's a different question, but it's also very similar. There are a lot of similarities between these two questions. And in fact, if I put both of the pictures there, it is the exact same arrangement of bridges. And this is where it gets kind of nice, because looking at these two different problems, one thing you might notice if you're thinking about these two different adventurers and their two different potential kind of paths that they could take through here. So for instance, the person on the boat could maybe do this kind of thing. But if they are able to do that, it means that those three bridges have been washed away. And if those three bridges have been washed away, then the person on the bank can't cross the river. So if there is a route through for the person in the boat, if it is possible for them to cross from the left to the right of the river, then it's, by definition, it's impossible for the person on foot to cross from one side of the river to the other. So these two kind of possibilities are mutually exclusive. They can't both work at the same time. And this puts us in a very particular type of situation, because sometimes this happens in maths, that you've got situations where if one thing works, then the other thing doesn't, and exactly those two kind of combinations fit together to make up the whole space of possibilities. So if the person in the boat can get through, then the person on the bank can't, and if the person on the bank can get across the river, then that means the person in the boat can't get through, because there's a chain of bridges connecting the north bank to the south bank. So this tells us something about this problem. And in particular, it's kind of hinting to me, because the way I would calculate for the person in the boat is very similar to the way I would calculate for the person on the bank. You know, I would look at the arrangement of bridges, I would look at which ones are knocked out, I would look at the different possible routes, but I would be doing a very similar set of thoughts and set of calculations. And in fact, if I look at this particular arrangement of bridges, if I say, here are the possible routes for the person on the boat, and then I look at the person on the bank, that is actually the exact same, it's the same graph, right? It's the same mathematical structure. And you know, if I need to find a route from one side of the river to the other, I need to find the same route from one kind of end of the river to the other. So in fact, not only do I have two situations that are mutually exclusive, so the probability of one of them happening plus the probability of the other one happening is the total probability is going to be 1, but also they are the same thing. So this forces the answer to be a 50% chance overall. This forces that there's no wiggle room here. They're both exactly the same. They're kind of symmetric, I guess. They're two problems that are symmetric. They're the same question, but we know that they add up to 1. So this kind of tells you that it is 50-50. And I guess if you do it the sort of complicated fiddly probability way and make sure that you exclude all of the cases where you've double counted and all of this, you do eventually get to 50%. But if you just kind of take a step back at it and look at the fact that you've got actually two very similar questions here, but with opposite answers, basically, is this possible is the same question as is this impossible, then it kind of forces this 50-50. And it's a thing that sometimes happens, and it's sort of described as a sort of symmetry in probability, I guess. You need very specific circumstances for this kind of thing to work, but it does happen in other situations as well, and it comes up in sort of simpler cases than this. So this was a really nice example of a puzzle. I think it was on like a Stack Exchange thread or something like that, because this is a great place to find little kind of interesting puzzles and things. But you can sort of take this to a very simple case. So if instead I ask a question like, I'm going to flip a coin. If I do 9 coin flips, what are the chances that at least 5 of those coin flips are heads, for instance? So this is something, obviously, there's a way to calculate this with probability and so on and so forth. But if you think about this, having at least 5 heads means that you don't have at least 5 tails. And if I was calculating the exact same question, but you replace the word heads with tails, because those probabilities are all the same either way, for each individual flip, it should be 50-50. Then that tells me that the probability of this has got to be a half, because at least 5 heads occurs exactly when at least 5 tails doesn't. And those two things are going to involve the same thing. And you can do, you okay? Yeah.
The screen, I think, might have frozen. You're still on the bridges.
That is really helpful. Thank you. I can't believe Zoom is doing this to me. It keeps happening. I mean, imagine a picture of a person flipping a coin and the words 9 flips and at least 5 heads. If you can imagine that, then you can see what's on my slides. I don't know. I'll just mime. I'll get a coin. I'll flip a coin here. Yeah. So yeah, this is a sort of simpler version of the same question, and you can extend it as well to things like decks of cards, right? Because this is obviously the next most complicated question in probability. So if you have a deck of cards and you're going to shuffle them, and you could ask a question like, what is the probability that the third card, having shuffled this deck, what is the probability that the third card is a club? And obviously your mind immediately goes to, oh, what are all the possible orderings? That's quite a lot of them. It's probably not worth checking them all. But what are the different combinations that we could have in, say, the first 3 cards, or this, that, and the other? But you've got to sort of, again, step back from this and think, okay, what if I ask the question, what is the probability that the third card is a spade? I would do exactly the same calculations as I would for clubs, because all the numbers are the same, and I would do the exact same calculations if it said hearts or if it said the other one, diamonds. So what that's telling me is that I've got 4 possibilities here, each of which is calculated in the exact same way, and the third card has to be one of those 4 things, which kind of forces it to be an equal split between the 4 different possibilities. So the probability of the third card being a club is the same as the probability of the third card being a spade or a heart or a diamond, which is a quarter. And I sort of discovered this, and I thought that is a really, really nice principle. And I imagine it crops up in lots of other places as well. And as I say, you have to be slightly careful that the situation that you're talking about, it does actually apply. But as long as you've got that sort of symmetrical probability calculation, then you can use this kind of thing. So I think I don't have a huge amount more to say about it, I guess. So this is a thing that I discovered several years ago, and I've talked about in various places since. I'm sort of interested to know if people know of any other examples of this kind of thing, or if they've seen this kind of thing happening in other places as well, because that's sort of interesting to know. And I'm also just happy to chat and answer any questions. So I guess that is my bit.
Well, thank you so much for this very interesting exploration. And someone mentioned that they love the number file pick in the background. And there's a question which is, conversely, if a question like this turns out to have probability 1/2, does it follow that there is symmetry arguments we might have missed?
That's a good question. Yeah, so if you're looking at a problem and you find the answer is a half, does that indicate to you that there's some kind of equivalent opposite problem that you could also be thinking about? I mean, maybe, yeah, maybe it's a nice way to, if you suddenly, if you find something calculates to be a half, that's maybe a clue that there is something going on like that. And I guess in general, it's good to sort of think about what if the question was this instead. And this is always a generally useful technique in maths. That if you're stuck on something and you're not sure what to do, try changing something and seeing if that makes it easier, or this is one of the sort of classic problem solving techniques, I guess. But if you're asked about clubs, think, is it hearts or is it spades or is it diamonds? Does that make it a different question, or does it make it the same question? And does that kind of give you a clue as well? But yeah, as someone has pointed out, equally, if the probability turns out to be a half, it may not be that there is a symmetrical, it could just be a half. Someone has asked, are there other arrangements of bridges and islands that have an intuitively deductible probability that isn't equal to a half? That's a good question. I have not explored that, but that's definitely a thing that could be explored, I guess. I mean, I wonder about the bridges of Königsberg, right? That's presumably one we can test. I don't know if there's Yeah, there could be three mutually exclusive equal probability events, maybe. It depends how many banks there are on the river as well. I guess if there's, like in Königsberg, there's like the top bit and the bottom bit, and there's a bit on the side as well, isn't there? There's three places you might be trying to get between. Yeah. Yeah, someone said they'll probably think about that at Maths Jam later on.
Well, the question about the symmetric kind of situation, it reminded me a little bit of a situation, for instance, in combinatorial game theory, where, for instance, to have a negative game is just to turn it horizontally or just to flip it, and this kind of thought about that.
Yeah, well, it's often a thing, isn't it? In game theory, you sort of think about what would happen if it was the other person's turn, and you take the inverse of the game somehow. Yeah.
Another question from the chat: who first asked these bridges problems mixed with storms and probability?
I don't know. Someone on Stack Exchange potentially, or maybe they saw it somewhere else. I'm not a recreational maths history expert, so I haven't researched it in that sense. I guess it's a reasonable enough question, that given a thing, can we introduce probability into it? And probability is a weird one because there's a lot of sort of counterintuitive things that don't quite work the way you expect them to. So you always have to be careful. But yeah, it's a nice mixture of sort of probability and combinatorics.
Speaking of mixture of the multiple ideas, there's a self-referential question, to which the answer on our side is of course yes, but which you might want to answer differently. So someone asked, could we ask math questions that are not necessarily related to today's topic? And this question is not necessarily related to today's topic, except it might be. Anyway, I think it's an interesting question.
I think the answer is, as long as you're not expecting a correct answer, because I can't guarantee that, but I can definitely talk about various things if you have other questions. Yeah, there's another comment. If there are other questions incoming, I'll give you some time to compose them. There's another comment that the symmetry of boating versus walking, compared to the specific arrangements that you've got, is interesting. That in this case you have a set of islands where boating is equivalent to walking because you get the same graph. If you kind of boil it down to the possible routes, and for which arrangements of bridges is it not symmetric? Is walking different to boating? Because I imagine you could easily create a scenario where you've got different graphs in both directions. Yeah, and equally, how does the probability of the storm affect it? So if there's a 25% chance of a given bridge being knocked out, how does that affect it? I suspect that probably also makes a difference, but I haven't played with it, so it's a good question.
Is there a known characterization of graphs like this self-dual? Another question.
Yeah, I think if a graph, because the dual of a graph is what happens if you join all of the arcs to, if you flip where the edges and the nodes are on a graph, you get the dual of a graph, and if it's self-dual, then doing that gives you the same graph back. Maybe it's something like that. Yeah, because I guess bridges that you can cross become bridges that you need to be able to get past, so you can't cross them. So it is sort of the dual. Yeah. And interestingly, because another person has mentioned that I do various online maths resources, this happens to be, would you look at that, it's a mug of my website puzzlebomb.co.uk, which is a puzzle website that I also run in my spare time. So we have a little kind of Patreon setup where people can sign up, and I think it's like £2 a month or something to get some puzzles emailed to you once a month. And it's a mixture of sort of maths and numbery puzzles and logic puzzles and some word puzzles and crosswords and things like that. But that's the thing that I've started doing with my other half, because in lockdown I can't do as many in-person talks, so I thought I would do something different just to fill up my time. So if anyone's interested in that, have a look at puzzlebomb.co.uk. There's some sample puzzles and things on there for you to have a look at as well. This
also answers quite directly the question in the chat: is there a job with these math puzzles?
Yeah, you kind of have to make it as you go along. I've variously been employed by people to make puzzles for things. So a couple of times when people have been doing like a show, I think someone was doing a show at the British Library and they said, we want to put some puzzles in the programme, can you write some puzzles? So I ended up doing bits of things like that. I've done kind of question writing for maths competitions and that kind of thing as well. And there's various, like New Scientist magazine has a puzzle column, and sometimes I contribute puzzles for that, which I get a little bit of money for as well. But it's, yeah, it's kind of piecework. It's not, there's not necessarily a full-time job in it. But cool.
Well, back to the problem. There was a question is in regards to how many islands and bridges and lots of boats or people. Does this resemble a pre-collision model?
Yeah, if you get it complicated enough, yeah, so it's sort of almost like a fluid dynamics thing that, you know, you've got particles moving around and each one moves to a particular place with a given probability. And yeah, if you've got a horrifically complicated set of bridges across a river, are you just looking at kind of the motion of fluids in space? I don't know. I imagine that fluid dynamics gets a lot easier if you're stuck to 2 dimensions. So that's, you know, in the real world, they have to do 3D, which is much harder.
And another question is the probability of, and this one is for pondering, is the probability of a bridge being out literally related to the probability of being able to walk?
Yeah, like, is that a linear relationship, I guess? No, maybe. I guess it depends on the bridge layout, but yeah, you could take a simple layout like this one and vary the probability and then see how that affects things. But it should still be 50-50, right? I don't know.
The bridges are independent. Another comment, the probability to cross the first bridge is 50%. If you have crossed the first, the chance to cross the second is 50%. If you have been blocked by the first, the second is no longer relevant. So the chances to cross the river, the chance to cross the river is 50%.
I think, yeah, I mean, it is, they are all independent, but it gets quite complicated because if you've got a 50% chance of the first bridge being out, but if it isn't out, you've then got a 50% chance, but there was a 50% chance, then another 50, so you kind of multiply them together. But even if you're just looking at the first 2 bridges, you could cross the first one and then the second one could be out, in which case you might be able to go across to the other island and then come down on the other side. So you know, I think it's just that there's a lot of combinations. Various opinions about whether it's not still 50-50 if the probability of each bridge being out is not 50%. That's, I honestly haven't explored it in that direction, so that's a good one to play with. Yeah, as I say, I've spoiled one specific puzzle for you, but obviously create your own puzzles. That's the usual method, isn't it? You know, you get given one puzzle and it suddenly becomes an infinity of different puzzles.
There's definitely a lot of wiggle room and playroom with this idea. I think we are starting to converge on comments in the chats. So I think we can just wrap up the session. And so thank you so much for this very mind-boggling puzzle, and that got us talking so quickly. And so yeah, bye.